All right, let's dive right in. Today, we're going to talk about the hidden systems that run basically everything around us, from something as simple as toasting bread to something as complex as guiding a missile to its target. So, have you ever actually stopped to wonder why your cheap toaster can totally incinerate your breakfast, but a thermostat seems to magically nail the perfect temperature every single time? I mean, think about it. One device just blindly follows orders, while the other one, well, it almost feels like it's thinking, right? It senses, it reacts, it adjusts. So, what's the big difference? Well, the secret isn't magic. It's all about engineering. It really just boils down to the type of control system that's built into the device. These systems are kind of like the invisible brains running things behind the scenes in almost every piece of technology we use. And today, we're going to break down the two main types, open loop and closed loop. I promise, by the time we're done here, you're going to start seeing these systems absolutely everywhere. You'll finally get the simple logic that separates a basic machine from a truly smart one. All right, first up, we've got the most basic type of control. I like to call it the set and forget system, because that's literally what it is. Once you give it a command, it just goes. There's no checking its work, no second guessing. It's a one-way street. And this is the most crucial part to understand. The result, the output, has absolutely zero influence on the original command. The system can't tell itself, hey, I'm overdoing it. It is strictly one-way communication. This diagram shows you just how simple it is. You give it an input, like, I want my toast cooked for 2 minutes. That signal goes to the controller, in this case, the toaster's timer. The controller then acts on the plant, that's just a fancy engineering term for the heating elements, and it produces the output, toast. The system never checks if the bread is golden brown or a piece of charcoal. It just runs the timer and stops, period. This analogy is perfect. An open-loop system is like a cook who follows a recipe to the letter, but never, ever tastes the food while they're cooking. They just assume if they follow the steps, it'll turn out perfect. And as any cook knows, that's a recipe for disaster. You are surrounded by these things. Your washing machine, it runs for a preset 30 minutes, regardless of whether your clothes are really dirty or barely worn. An electric hand dryer just blows hot air because a sensor sees your hands. It has no idea if they're actually dry. And a light switch, it stays on until you physically turn it off, even if the sun is blazing through the window. So what's the trade-off here? Well, it's pretty clear. They are simple to build and super cheap to produce, which is a huge advantage. But the price you pay for that simplicity is a lack of accuracy and reliability. They just can't adapt to anything unexpected. So let's look at how the other system fixes this. Okay, now we get to the cool stuff, this self-correcting system. This is where technology really starts to feel, well, intelligent. And it's all because of one secret ingredient. And that's it, feedback. It's the ability for a system to measure the results of its own actions and then report that information back to itself. This one single concept is the foundation of basically all modern automation. So, unlike its simple cousin, a closed-loop system is constantly checking its own work. It measures the output, it compares that to the goal you set for it, and if there's a difference, an error, it actually adjusts its own actions to get closer to that goal. Let's trace this out, because this is where the magic happens. Your input, let's say you set the thermostat to 72 degrees, goes to a comparator. At the same time, a sensor measures the actual room temperature. That's the output, and it feeds that information back to that same comparator. So if the room is, say, 75 degrees, the comparator sees the difference and generates an error signal. That signal tells the controller, hey, we're too hot, kick on the AC. And this whole loop just keeps running, making tiny adjustments until that error is zero. And there's the perfect contrast. This isn't the blind recipe follower. This is the expert chef. They don't just follow the recipe, they taste. They compare that taste to what they want it to taste like, and they adjust. That right there is feedback in action. And of course, these systems are also everywhere. Your home's air conditioner is the classic example. An automatic iron turns its heating element on and off to maintain the exact temperature you picked. Your car's cooling system is constantly working to keep the engine from overheating. And yeah, even a missile tracking system is just constantly comparing its position to the targets, making thousands of micro adjustments to stay on course. The benefits here are crystal clear. You get high accuracy, real automation, and reliability. But all that sophistication comes at a price. These systems are way more complex, which makes them more expensive, and definitely harder to design and maintain. You're adding a bunch of extra components like sensors and comparators. So let's put them right next to each other. Let's do a little head-to-head showdown and see how they really stack up. This table really says it all, doesn't it? If you need something cheap and simple and you can live with it not being perfectly accurate, open loop is the way to go. But if you need accuracy and reliability, if the result truly matters, then you have to accept the complexity and cost of a closed-loop system. It's one of the most fundamental trade-offs in engineering. So, why did we just spend all this time breaking down diagrams of controllers and feedback loops? Because this isn't just about toasters and thermostats. It's much bigger than that. And here's the main takeaway. Understanding this one difference, the concept of a feedback loop, is really understanding the giant leap we took from basic machines to the automated, responsive, smart world we live in today. It's the difference between a simple tool and a truly responsive system.
Think about it. The cruise control in your car, the autopilot in a plane, the systems that balance our entire power grid. They are all just running on feedback loops, constantly measuring, comparing, and correcting. So the real question to leave you with is, now that you can see the pattern, how many other hidden loops are running your world right now?